Another test that we have is called root test. This test is going to be useful when the terms in the series that we have looks like we have something raised to the n power, we have something to the n power, we have something to the n power, like we have in the examples down here. So the way this root test works is that if I have a series where the terms are positive, then I can compute the limit of the nth root of a sub n. If this limit is less than 1, then I can conclude that my series is going to converge. If this limit is bigger than 1, then the series is going to diverge, and if the limit is equal to 1, then I can't really tell. So if we look at the examples that we have down here, now this guy looks like the sum of something raised to the n power. So if I try the root test, I'm going to compute the limit of the nth root of the terms in my series, which is just 3 over n plus 1 raised to the n power. 3 over n plus 1 raised to the n power. So now then the nth root and the n power get cancelled out, so I'm going to be left with the limit of 3 over n plus 1 when n goes to infinity. And now as you can see, when n gets really large, this guy is going to get really large. 3 divided by something really large, I'm going to get 0. And 0 is definitely less than 1. When the limit of the nth root is less than 1, then I can conclude right away that the series is going to converge. So this guy is going to converge. Now let's take a look at the next one. Again, I have something raised to the n power, so I'm going to compute the nth root of the terms of the series, which is n plus 1 over n to the n, and take the limit when n goes to infinity. Now once again, the nth root and the nth power get cancelled out, so I'm going to be left with the limit when n goes to infinity of n plus 1 over n, and this guy is gonna just equal to the limit when n goes to infinity of, let's see, 1 plus 1 over n. So when n gets really large, 1 over n gets really small, so I'm gonna get 1 plus 0, which is 1. Now, this limit of the nth root is equal to 1, so this belongs to the third case where if the limit of the nth root is equal to 1, then I can't really conclude anything. So this guy may converge or diverge. So the root test is inconclusive. However, so once again, we have a series and a test. It looks like I can try the root test, but it just doesn't work. So once again, I'm going to come back to this example in the example, let's see, 4.8. So I'm going to come back here again. Now let's take a look at the next one. Well, I have the series 1 over 2 to the n and the series 2 to the n. These two guys are actually just the geometric series. So we knew right away because the ratio in this one is 1/2. So I know that this guy is going to converge. This guy is going to converge. And for this one, the ratio is 2. So I knew that this guy is going to diverge. But then let's try to verify this using the root test. If I want to use the root test, I'm going to compute the limit of the nth root of the terms in my series. So the nth root of 1 over 2 to the n is just going to be the limit of 1/2. And the limit of 1/2 is just going to be 1/2, which is less than 1. So this belongs to the first case where if the limit of the nth root is less than 1, then I knew that the series converge. So that coincides with what we have earlier. And for the last one, if I compute the nth root of this guy, once again, it's going to be the limit of the nth root of 2 to the n. Then I'm going to get, let's see, the limit of just 2. And this is going to be just 2, which is bigger than 1. So I can tell that the this guy is going to diverge because the limit of my nth root is bigger than 1. So basically, we can use the root test on the geometric series as well. And notice how the cutoff value, less than 1 and bigger than 1, this is actually the same cutoff value that we have when we want to decide whether the geometric series converge or diverge if the ratio is less than 1. If the absolute value of the ratio is less than 1, then it is going to converge, and if that is bigger than 1, then it is going to diverge.